Good evening. Welcome to this evening's webinar, Specialist Mathematics Topics of Kinematics and Solids of Revolution. Your presenters this evening, Stephen Crouch and Sanjeev Meston. Good evening, Stephen.
Good evening, Brian. Good evening, everyone.
And good evening, Sanjeev.
Hi, Brian, and hello, everyone.
Great to be working with you both again. Stephen, I was hosting a webinar for just last week, and Sanjeev in recent times, and also working together at conferences. I've looked at the material that both of our presenters have prepared for us this evening, and I can assure all participants you are in for some great stuff. My name is Brian Ladwater there. The way the event is set up, Sanjeev is going to firstly take us through volumes of solids of revolution. I particularly like this topic myself. As I said, I've looked through the material that has been sent through, and I for one, will be using this with my students this year. I teach this in an engineering diploma calculus course, and so Sanjeev, thanks for your slides and CNS files. I'm going to be using them this year. And in the second part of the webinar, Stephen Crouch will be taking us through kinematics. Okay, without further ado, we'll hand over to you, Sanjeev.
Thank you, Brian.
We can see your screen and it's looking good.
All right, thank you. Our focus topic for this evening is solids of revolution. And first part of this webinar, I'm going to look at graphing of 3D shapes, and then the second, determining the volume for solids of revolution. This is what the study design states for the VCE Specialist Mathematics course. So that's on your screen at the moment, the brief from the study design. And just a brief introductory screen over here, what solids of revolution are. And we are basically going to rotate this shape, which is sine of 3x plus 4 in a domain of pi by 2 to 3 pi by 2. And we're going to rotate it about the x-axis. And in doing so, actually, we'll obtain a solid shape. So if I go to the next screen, that's the actual curve, and we see a 3D graph over there for the same function there. And that's the result of rotation. Now, in the second, Brian, can I get rid of this I'm displaying on my screen? How do I get rid of that?
We've got the PowerPoint. We can see your PowerPoint. You're wanting to swap to your calculator?
No. What I'm seeing, your name on my screen. Although you may not be seeing it.
Okay. Yep. In that tab to the top left, there's a little tab in the top left of that box. If you click that, it will minimise.
Anyway,
looks like a little. We can't see it. It's not coming through on the participant screen, but I can see that it can be a distraction.
It's blocking my view on the screen.
Yep.
It's sitting right in the middle.
Yep.
Yeah.
Look at that box. Look at that box. When you see,
go ahead anyway. So you can see both the. There are two shots I've got over there. In the second one, you can actually see the function in blue sitting on top of the solid.
We can see that all very clearly.
Okay, so when we look at the solids of revolution, we are going to look at the method of rings or disks, and there's also the method of cylinders, which we will not cover in this webinar because I haven't seen many, or rather I haven't seen any question using that method in our exam, so I'll skip that. And then we're also going to look at volume enclosed by two curves when they intersect. So the same function that I had, that sine of 3x plus 4, you can see the result of revolution. And we can see that the volume is 162.84. And later on, we're going to see how to obtain that. But that's the rotation part, and I've done all that on the CAS, and we'll show you later how to get those shapes. So that's just a video file of the same thing that I've done, and that's rotation about the x-axis. And now you see the same function rotating about the y-axis. And I've just changed the orientation. So again, change of orientation.
Yeah, around different axes. So
yeah.
You've got 3 to choose from. I like it.
Yeah. So now how to do a 3D graph of the function on our CAS. So obviously we have a function that we define as fx, and if you look at that to generate a surface of revolution of any 2-dimensional scalar function, the TI expects us to use t as a parameter and u as actually an angle parameter. But we can actually swap the two, and I'll explain that later when we actually get onto the calculator screen. So basically, we set the parameter as t, and then u is the projection angle on the 2 axes. So that's the on the y-axis, if I'm doing that, that's the function times sine of u, and u is the projection angle. And if I'm doing on the z-axis, then it's again the function times cos of u. So it's always going to be sine u and cos u, the multiplication factor. So t is the parameter there when I parameterize the function. That's the projection in the y and the x-axis. And the next screen will explain what really is going on there. So I've got this function sine of 3x plus 4. So we are saying let x equals t. And that will actually, on your CAS screen, go over there. Now, just to quickly show you what I've done there, if I go into my calculator, to do a 3D graph, I insert a graph page. So that's inserting the graph page. And once I've got the graph page, if I go to menu, I'll see an option of view. And under view, you'll see 3D graphing. And I'll see that. Now, that's actually in the Cartesian. If I want to go to parametric, I just right-click, graph entry, and there is an option for parametric. And the moment I click parametric, I get this option. And that's where I enter my function. So that's in the x parameter, that's the y in the parametric form, and that's z in the parametric form. So if I go back to my PowerPoint, that's what I'll put in the x box, that's in the y and z. Now you'll see it says t and u in the bracket. So those are the 2 parameters. So t is actually replacing x, and u is the angle which we are projecting. And I'll explain that later when we actually do a few curves or functions. So I've entered that on my calculator screen. So instead of x now, I've got sine of 3t plus 4 times sine u. And again in the z axis. And of course, so as a result of that, I actually do get this shape. Now, I've obviously made some changes to the settings, and if I right-click that, you can actually see it gives me. Oh, so I'm on the PowerPoint. Sorry, I should go to the calculator page.
On the calculator, yep.
Yeah. So if I
change the box dimensions, yep.
If you look at that, it really gives me the option to edit the parameters. What's the minimum value for t? What's the maximum value? And that's the rotation. I would normally put rotation from 0 to 2 pi. And t is basically the domain that you want for the x-axis if you're rotating in the x-plane. So, you know, if I'm going from 2 to 5, I'll replace t minimum by 2 and maximum by 5. So that's what I would do. So if I go back here, that's the graph I had. If I do Control G, it will actually take me to what I have over there. So you can see the functions that I've got. And if I right-click, I can change the color, I can change the attributes. In attributes, you can actually set the resolution and so on. And if I actually click on the graph there, it lets me adjust the range and everything else. So we'll look at that in the later screens. So back to my PowerPoint there. So that's how I would enter the function. So that's a graph on the TI-nspire, and it really looks nice once we have set the aspect ratio and we've got the correct range. So that's what you would be typing in on your screen. So I've got that enlarged so you can actually get a good view of what we are typing. Now we'll try that with another function.
You had the T on the X parameter. That will be for a rotation around the X-axis. Am I right?
Yeah, correct. So if I put it on the Y, then I'm rotating it in the Y-axis. Yeah, I was going to come to that later. I'm glad to ask that question though. Yeah. All right. Now, if we look at this shape over here, I've got in the X-axis, I've got 30 cos T. Now, in this case, I'm actually trying to rotate along the Z-axis, and I've used the parameter 10 sine T over here, and then of course in the X I've gone times sine U, and in the Y times cos U, my function. Now 30 over here actually represents the radius. If I had all three set to 30, I would actually get a perfect sphere. So where I've got 10, if I had set that to 30, I would get a perfect sphere. Now I've changed that to 10. So can you predict the shape? Of course, I won't be able to hear you, but what you will get would be a shape like this. So I've got the values, in the graphing bar that you have entered, and this is the result we have got. Now, if you look at the next screen here, I have changed it to 50. So 30, 30, and 50, and I actually haven't intentionally adjusted the window size because I actually wanted a barrel this time. So here I've got a barrel. And if I want to see the complete shape, I've got this 3D range settings now. All I need to do is to change the minimum and maximum value because I've got 50, so I need to have my minimum as a value greater than 50, when I say less than negative 50, and maximum as a value greater than 50, which is 55. So I've just changed my settings, the range settings, and now if I go to the next screen, I'll actually see the same shape in the entire screen. And that's what we get over there. And now you'll see I've got actually on the screen over here, the resolution, I can change that. So the first one is the resolution, the last one is the transparency. So that's making adjustments. You can get rid of the mesh if you want when you click on that. So if you want me to just demonstrate that, I'll do that here. If I go to attributes, and if you look at that, it's at the moment got the surface and wire. If I click that, that becomes surface only, and if I click that, it becomes wire only. So I can adjust the settings there. And if I click here, it tells me that's the resolution of T. That's the resolution for U, and that's the transparency or the opacity. You can adjust those values there. Okay, going back to the PowerPoint, I've now inserted a slider, and I've just changed the function. It's still a sphere, but I've inserted slider, and I've got values A, B, and C. And now with the slider, I can change the values for A, B, and C. At the moment, I've got all three set at 80, and I've got a perfect sphere on. You can see that, and I've changed the color to black and white, and you see like a crystal ball over there. So we can do actually a whole lot of interesting things with these 3D shapes. Okay, I don't want to make that the focus of our learning today because I want to go to the finding the volume aspect as well. So let's go on to the next screen. Okay, it's the same shape, but you will see over here U minimum and U maximum. I've gone from negative pi by 8 to pi by 8, and you'll see when I enter the values as pi by 8, it will approximate it to a decimal. And T, I've gone from 0 to 2 pi. So I can obtain shapes like this. and I've still got A, B, and C set to AT. So that's part of a sphere that I've got out. All right, we've got another function here, and the original function is x minus 4 to the power of 3, so it's a cubic plus 9, and the domain is 2 to 6, and I'm going to rotate this in the x-axis, and then I'll do the same by rotating it in the y-axis. So first, let's see how to graph this. So this time, I've got my parameters u, and as Brian said earlier, I could actually swap u and t. It doesn't matter what I put over there, but then the projection angle will become t if I'm using u as a substitute parameter. And because I put it in x, that means I'm rotating this shape in the x, about the x-axis. If I put this over here in place of y, I would be rotating it about the y-axis. So this is rotation about the x-axis, and this is what I enter. So I'm not using x anymore. I've replaced it by the parameter over there. So you get the shape, and then I've adjusted the range settings. For 3D graphing, you won't actually see window size. You'll see the range settings. So that's what I obtained, and this is just the same shape. I've zoomed in on the shape, and over here it's just running automatically. So that's the video file there. That's rotating the same shape about the y-axis. So all I have done is, the parameter u, I've now gone and put in the x-plane. Okay. Volumes of solids of revolution using the ring or the disk method. So this just explains basically what anti-differentiation is. I won't spend much time. This is using the rectangle method and how we approximate the value if we are finding the antiderivative. So I'll skip that bit there. So obviously we are increasing the value for the area under the curve by having more rectangles, and then the width of the rectangle, when it approaches 0, we are getting a more accurate value, and this is the logic we are going to use to find the volume as well. So that's what an antiderivative does. We find the area under a curve, and that's the mathematical logic there. So what we are doing is we are making this, interval A to B. We are splitting it into n number of paths, and the more the number of paths, the smaller that interval becomes. So as n approaches infinity, we are saying delta x approaches 0, and the delta x then becomes dx over there. So the dx actually represents the width, which is approaching 0. So that's finding the antiderivative, and we are going to extend this to volumes. So what we do is we've got a shape here, and we assume that shape is made of several disks. And what we want to really do is minimize the width of the disk. So that B to A is the volume we are measuring, and I split that into n number of paths. And what we see on the screen are those n number of disks in that case. So that's the math behind it. And eventually, so as I said, I'll skip that. So we obtain the formula. So I've got volume. If we are rotating in the x-axis, that's the formula from A to B, that's the interval. So that's the radius, so pi r squared dx, and then if we are rotating in the y-axis, that's the formula there.
I really like the progression there, Sanjeev.
Yeah. Thank you.
The rectangles for areas and then the disks for volume. It makes absolutely beautiful sense. Yeah.
Yeah. All right. So now what we have got in the bracket is, the function value at x is actually giving us the radius of the disk at that particular point, whatever the value of x is.
Yes.
And that's rotation in the x-axis, and the one in red is the rotation in the y-axis. So you'll see actually we are using the concept of finding the inverse of a function and doing that.
Yep. And of course we square it because it's r. Yeah. It's r squared. Yep.
R squared. Yeah. Okay. So if we did this now, I've got a function x squared minus 3x plus 3, and we want to find the volume of this solid when we rotate it about the x-axis, and the domain is 2 to 6. So you can actually on the screen see what the shape would be when you rotate it about the x-axis, and it says the volume would be about 1,309 approximately. So that's the approximated volume. Now I'm going to actually use the list and spreadsheet method first. So I've defined the function here, and you can use a notes page. I prefer using a notes page. So I've defined the function here, and I've actually created a list and spreadsheet page, and I've actually assigned a value to dx. At the moment it's 0.02. So let's go to the actual calculator, and I'll show what's going on there. So that's where we are. I've defined the function. We go to the list and spreadsheet page, which is there. Now I'm going from 2 to 6. So I've actually generated a sequence in terms of x. So the variable is x. I'm going from 2 to 6, and dx is actually something that I defined previously in my other screen, and I had set the value at 0.2. So you'll see the sequence it generates is 2, then 2.02, 2.04, and so on, and it will go up to 6. And then in the next column, we are actually finding the function value, which is actually giving us the radius. That's why I've called RAD over there. So that's giving me the radius. And then in column 3, I've used the formula. And I'll take you back to the PowerPoint, and you'll see actually what the formula is. If I click there, right at the bottom of my screen here, you'll see it says pi times the square of radius times the value of dx, and dx at the moment is set to 0.2. Now if I go back here and I change this to 0.1 and click enter, it's actually giving me an approximated value. But if I go back to my table, you'll see it's updated. So that's 2, then 2.01, and it's giving me the radius, and that's the square of the radius times pi into the value of dx. So that's actually giving me individual volumes. Now what I need to do is to sum that up. So if I go back to my screen here, I've got over there sum of the variable that I had defined in column 3, which is volume, and it gives me this approximated value. So if I change this value here to 0.05, it's going to actually be a bigger approximation. So you see it's 1344 at the moment. And if I go and put 0.01, it's going to give me a more precise, sorry, what happened there? Sum of volume. There's something gone wrong there. Okay.
Yep, if you pressure, yep.
Yeah. Anyway, so let's,
yep.
Yeah. And if I put 0.02, you can see it's giving me a bigger error because the answer I'm expecting is 1309 instead of 1323. All right. So that's using the list and spreadsheet method. Here I've actually done the same thing slightly differently. I've defined the volume function over here. The volume of the function, and that's A is my lower limit, B is the upper limit, and N is the B is the upper limit, and N is the number over there. You know, that interval A to B is being split into how many parts. So at the moment, I've set that 2,000 parts. I'm going from 2 to 6, and if I say action, evaluate, it will say done. That means it's accepted my, and now if I go and do that, action, evaluate, it gives me an exact value. Now I've used the round feature there. Actually over there itself I could do action, evaluate, approximate, and it gives me an approximated value of 1312. Now if I change the number of interval there, if I change that to 100, obviously, yeah, it's going to be, so it's moving away from the exact value. So it really depends on the number of, and that's the logic that is used there. So approximate.
Just on those math boxes, often a quick way to calculate all of them is if you select them all. So you can do a select all, either with the cursor, and then in the menu, there's a calculator.
Yeah.
Yeah. So I just thought I'd point that one out. Just the notes pages are just so useful to use.
Yeah. Okay. You'll see I've used a syntax over here round. So I've used the formula. So same thing exactly. Now I've got over there round to 2 decimal places. So that comma 2 will round off my answer. Now I don't have to do approximate or anything. Now if I just do evaluate, because I've already approximated that, it gives me an approximated value to 2 decimal places. So all I need to do now is probably go and change that to maybe 2000, and I should get a better value there. It's getting closer to 1310. Of course, now I need to rush through. So that's actually using the actual formula, which should give us the exact value. So if I use the formula, and once again, let's go and approximate that. Okay. I've got a problem here now. I won't go through every single step because we're running out of time, but that's the same logic we have used there. Let's go to this problem here. Okay, the problem is on the PowerPoint. So Alt-Tab.
So we're using the intersection between 2 curves? Yep.
Yeah. All right. So let's go quickly here. I've skipped to that. Okay. So we are looking at this function here. Determine the volume of solid shape obtained by rotating. So that's my first function, and that's the second function, which is obviously a straight line. And we are rotating it, I think, in the y-axis. Yeah. So we are saying it lies in quadrant 1 and rotated about the y-axis. So what we have to do is to find the inverse, or rather, just swap x and y. And if I do that, that's what it becomes, the function. And I get my points of intersection, which are 0 and 9, and I'll show that in the next screen. And this time I'm integrating it with respect to y, because I've made y my variable. And that's if they were to work it out by hand, but here, that's the shape we have got. So my points of intersection for the y value are 0 and 9, because I'm rotating it about the y-axis. That's why I've taken the y values. And that's the 3D graph for that on our CAS. And if I was rotating it in the x-axis, that's the shape. And you can actually clearly see the inside and the outside. I've used 2 different colors, and I've used the transparency factor. So you can actually see that there are 2 shapes, and that's the shape we are really looking at. And then we are determining the volume of this rotated about, I think it's the x-axis I've got, or the y-axis, yeah, because my screen is getting covered. So let's see what happens.
I like the transformation there.
Yeah. That's the square root function, and then I've got the line there. Now, what you will see actually says over there, when rotated about the line x equals -1. So what I have to do in this case is I want to rotate it about the line x equals -1, but if I move everything to the right, if I do a horizontal translation by 1 unit, actually I'll be rotating it about the y-axis, and both my functions will also move 1 unit to the right. As a result, the volume is not going to change. So in this question, all we are doing is we are doing actually a horizontal translation. And if you look through the working, I've got that here. That's the working there. And we should obtain a volume of approximately 20.18. And that's on the CAS. And so CAS gives the volume of 20.16. So I just quickly want to go back to this over here. That's the result of rotating it. So that's the curve. So we need to find the points of intersection, and then I've entered that in the CAS. So that's, once again, the function is, there are 2 functions. So that's the second function, and that's the first function there. And we are rotating in this case about the y-axis. That's why I put the variable t there, or the parameter t, and we obtain that shape. Now, Brian, these files are available for everyone as PowerPoint, and of course the TI files are there as well. So teachers can actually directly use this for teaching in the classroom. They can obviously make edits, but it's ready to teach from here straight away. Thanks, everyone, and over to Brian.
Absolutely. Yep. Thanks, Sanjeev. And as I said, I will definitely be using this with my calculus class this year when I teach that topic. I'm just following up a couple of questions that we had in the chat there. On those 3D graphing pages, I'm just waiting for this to appear. On those 3D graphing pages, when you get Sanjeev's document, TNS document, can I encourage you to see how they're built? Because I actually went through all this today to see, hang on, what's behind all this? So you'll just navigate to a page, okay, and if we've got, I really like that spreadsheet one, by the way. If we've got a 3D graph here, to see what's going on, hit the menu and go to the third option here, 3D graph entry edit. Take it from function to parametric, okay? And that opens up the what's normally the function editor, but of course it's parametric equation editor here, and we'll arrow up and you can see what's going on there. So that's the three parametric equations that were entered, and see this three dots on the side, edit parameters. Click on that and you can see what's going on there. So we've gone from 1 to 17, and then from 0 to, for t, and then from 0 to 2 pi for u. That's really worth looking at. So getting some comments coming in there, Sanjeev, saying that they really love the sequencing of what you did there, and I think this would unfold beautifully with a class. So that's why I'm going to use it.
For keeping things rolling smoothly. Thanks also to Sanjeev for an absolutely incredibly amazing presentation over there. There's certainly those files that I will use when I get to teaching that revolutions topic in my classes. I haven't gotten to that yet, so it's perfect timing. Okay, so with my section of the presentation, I'm basically going to be showing you how we use the CBR2 to talk about kinematics with our classes. Now the CBR2, some of you might have used it before, some may not. So in my presentation, I'm just going to go through a few basics, and what's going to happen is at the end, I'm going to show you a quick demo. I'm actually going to use the CBR2. I've got it sitting right here. I'm going to show you how to use it to collect data and also analyze that data. Okay, so let's make a start then. So first of all, the CBR2, as you can see, it's this nice little device over here. It's absolutely amazing in the sense that it's really compact, and it gets your motion data collection going without any crazy big, expensive, complicated setups. It's a single device. You plug it into your calculator or your computer. It's basically, the CBR is short for calculator-based ranger. You can plug it into a TI calculator, or you can plug it into a computer. So today I will be plugging it into my computer to get some data collection going. You can of course plug it into a calculator too, and then make it portable that way. In basic form, what it does is it uses a sonic motion detector. So it sends sonar sound waves back and forth, and it uses the timing of those events to figure out the position, velocity, and acceleration of your particular object. There's actually a really good guidebook that Texas Instruments has produced. And if you'd like to check out that guidebook and get a more in-depth explanation of the CBR, then feel free to go to that particular link over there. I've created it especially for the presenters of, for the attendees of this webinar. It's very easy to remember. So just bit.ly CBR2 guide. So if you'd like, after the webinar or at any stage you prefer, you can certainly check that out. So I'll just quickly walk through how the CBR2 can get set up. Basically, you just need 4 AA batteries. You've got your cable that connects the CBR2 to your calculator, and of course you need to have your calculator there. In terms of calculators, you can either use an nspire CX-CAS, you can use an nspire CX, you can also use a TI-84. There's quite a few calculator models, but those are the main ones that it works most well with. Once you've done the setup, this is basically what it looks like. So that sonic sensor that you see over there, it actually opens up, it swivels between 0 and 180 degrees. So you take it from here and you can swing it all the way back, depending on what you're looking at. So here it is swiveled 90 degrees, and what it reveals is a little switch over here, and I will explain that switch shortly, what it does and how to use it. Here's a diagram of the cables. So this big square cable goes directly into the CBR2, and this small cable here goes directly into your calculator. So when you do plug it in, typically what actually happens is as soon as it's plugged into your calculator, the calculator straight away recognizes that the CBR2 has been plugged in, and it actually opens up this Vernier Data Quest application on your calculator. If not, of course, you can then go straight here, and then it'll open up the data collection screen, which looks like this. So this is a picture of the CAS calculator connected to the CBR2, and if you look carefully, I think I can see 0.547 there. It's measuring about half a meter's distance between that sonic sensor and whatever object that was placed next to it. So as I said before, there's a sensitivity switch that is underneath the sonar detector, and that is basically, it sets the sensitivity of the data collection. So there's one for dynamic tracks and carts, and the sensor is less sensitive because you're dealing with sort of larger objects. You don't need too sensitive of a data collection to happen, so it's a bit less sensitive for that. If you're doing more slower things, such as walking or bouncing balls or looking at a pendulum, etc., those sort of activities, you then switch it over to the normal mode. However, sometimes what happens is when you're on the normal mode, the sensor happens to be too sensitive, and you actually have to switch back to the track mode if you're getting a lot of noise in the data. So if you're getting some data and then you keep seeing this noise or spikes or random spikes and that sort of thing, it's best to switch back to track, and then the sensor becomes a bit less sensitive, and then your data goes back to normal. Another thing to be wary of as well is there's something called the clear zone, and that is somewhere between 15 centimeters and about 6 meters. So the data collection can still occur between 0 and 15 centimeters. However, you can't rely too much on the accuracy. There tends to be a lot of noise and spikes that happen if you do a lot of data collection within that 15 centimeter sort of non-clear zone. So your best bet is to be from 15 centimeters onwards. It's very rare that you need to go all the way to 6 meters. When I use a CBR, I find that I find myself between 15 centimeters and about 1 meter. For most practical purposes, that suits you. Okay, so of course, don't measure any objects within 15 centimeters from the sensor. So here's a few ideas for activities that you could try if you've got a CBR2 and you want to show, you want to demonstrate the ideas of kinematics. So one of the ideas is you set up the CBR stationary on a bench, and you try and sort of set it to about waist height. And what you can do is you can set it there, begin your data collection, and start walking backwards and forwards between the sensor and a wall or the room or whatever it happens to be. What the data will do, of course, is it will create a graph that looks something like this. So if you start close to it and then you walk backwards, the distance between you and the sensor increases. And if you walk back closer towards it, the distance between you and the sensor decreases, and then you get that graph there. Of course, that brings in more ideas about, okay, how are we graphing position versus time? And then you can extend that discussion over to looking at velocity, acceleration, etc., etc. Then there's another one that you could do, which is called match the graph. I will actually show you a demo of this one as well. This is really nice in the sense that what the calculator does is it actually gives you a graph. So it basically creates a simple sort of graph of position or distance versus time. And when you start your data collection, you actually try and match the graph as close as possible. So this further gives the idea to students that if I've got this particular graph or this set of data, how would you run an experiment so that your data matches the one shown on your screen? It's a really nice activity like that. I've run this sort of activity a couple of times with students, and they love it. They want to go do the same thing 5 times, 10 times, whatever, until they get it perfect. So it breeds some really intense competition, but it's awesome seeing the students enjoy themselves doing calculator, data collection, and physics sort of ideas. So here's a sample. There is what the calculator gave, and the dots here that look a bit wonky, that is what the student had produced. So another activity you could use is, of course, a swinging pendulum. Now, whilst this is not really a kinematics topic, it certainly does give rise to trigonometric functions. So that right there, that's my computer there with my application open up. There's the CBR, and here's a ribbon with this tiny little ball set next to it. And this is the CBR setup with the ball next to it, of course. And of course, as the ball swings away and towards the sensor, that distance there, the 0.131, as you can see, that will of course increase and decrease, and the calculator will plot that data. Of course, using a small ball may not be the best thing to do, because you don't want to muck up the data with external movements that are occurring. So of course you can actually use a fishing float, as good old Peter Fox demonstrated to me a while ago. So if you take a nice big fishing float and you put a string or a rope through it, and then you swing that in front of your CBR2, you can actually get some really nice data coming out of it. Especially if you only look at about 3 or 4 swings, air resistance hasn't had a chance to set in and completely wreck the data yet. So you actually get some really nice data coming out of it, both in terms of position and velocity. And this, again, gives rise to great ideas about the difference between position and velocity. And you can, of course, then do a regression on that and get a sinusoidal or a cosine curve on that, and therefore do a differentiation and get the velocity, etc. So there's many ideas from position, velocity, acceleration, even all the way to differential and integral calculus that you could introduce using real-world data that you and the students can collect during class time, or even during an incursion, excursion, that sort of thing. Okay, so as a demo, what I'm going to do is I've got my CBR2 set up as it is, as you can see right there. It's lying flat on the table. I've got a maths textbook that's hovering above it. And what I'm going to do is I'm going to move the textbook upwards away from the sensor. And I'm going to graph the position of that book with respect to time. Okay, so here's a couple of dot points as to what I'm doing. So of course I'm going to start by getting the position time data, and then going to determine the line of best fit. And then after that, I'm going to try and attempt a position match, and let's see how good the position matching skills get. Okay, so over to my calculator. So I've got my CBR2 connected. I'm going to go and add a Vernier data quest. There you go. There it is set up. Currently, I'm holding my book about 17 centimeters or so above the sensor. What I'm now going to do is click the play button, which is going to start the data collection, and I'm moving the book up at a pretty steady pace. There we go. So what you can see here is the position of the book is increasing with respect to time, as I mentioned before. Now, of course, my hand is not as steady as I hoped it would have been, so the data does look a bit jagged. So, of course, I can actually perform another run, Okay, so I'll start another one here. And it's going up, up, and up. And there we go. We're getting a bit of noise in data. So as you can see, depending on the parameters that you choose, you can actually choose different sort of things, different numbers to help change the parameters that you're using in the data. So one of the things is the rate of the data collection that you're doing. So first of all, your rate of 20 samples per second. Of course, that means there's going to be 20 data points collected every second. And then the duration of 5 seconds. That says that you want your experiment to last for a total of 5 seconds. So you can, of course, change that 20 to be a larger number if you want more sensitive data. And if you want your experiment to go longer, you can, of course, change that 5 to 10 or 15 or 20, whatever you prefer. So the 20 and the 5 are the default settings. Of course, you could change them to whatever you like. And then depending on what you get, you can then analyze the data efficiently. So again, I'm going to try a second time. This is going to be my last attempt. Hopefully it works with better this time. So it's about 16 centimeters. I'll start the data collection, start going upwards, and there we are. I guess that doesn't look too bad. Of course, the velocity data looks quite chunky, and that's because the sensor is, of course, quite sensitive. So because I was using my hand to raise the height of the book, any sort of kinks in the data show up quite amplified over here. Anyway, so once you've got data, what you can do is you can right-click or control menu on the handheld, and then just go to Analyze, and then you can go to Curve Fit, and then you can perform any one of these regression models to it. Of course, I'm trying to go for a linear model, so I go linear, and it's gone and done a regression on that. So as you can see, the gradient is 0.09, so that refers to a rise of 0.09 meters, or in other words, 9 centimeters per second. So the speed that I was rising the book was 9 centimeters per second. The B, which is the y-intercept, is 0.14. So that tells us that when the data collection started, my book was a distance of approximately 14.2 centimeters from the sensor. You can, of course, then look at the R and R squared values to see how close of a fit that linear model is compared to the data, and that looks quite good. I'm quite happy with that. You can then actually go and do further analysis with it. You can actually go to Doc, Insert, and I'm going to insert a data and statistics page. And on the x-axis, I'm going to put the time. On the y-axis, I'm going to put the position. As you can see, you get the same graph over here. And furthermore, you can also do another regression analysis to this. So you can go Menu, Analyze, Regression, again, do a linear regression. And this time, we get a sort of more decimal places in our data. And then you can actually take that line there, open a calculator page or any other page, and do more analysis to that. And then you can introduce the idea of a velocity being the gradient of this, and then you recall your knowledge back to y equals mx plus c, and the fact the gradient is 0.09, and how that ties in with the speed. So as you can see, the CBR2, even though it's a small and tiny device, it's incredibly powerful in what it does and the sort of discussions you can generate out of that. Okay, so what I want to do now is I wanted to do a data match, like I was saying before. So a data match is where I'm going to ask the calculator to, I'm going to ask the calculator to provide me with a position graph, and I'm going to try my best to match that. There we go. Ooh, that's probably the toughest one I've ever gotten. Okay, I'm going to try my luck with this, and let's see if it goes well. So as you can see, we need to start with quite a high velocity, then slow that down, then go in the reverse direction. So I'm now holding my book, as you can see, about 17 centimeters over here above the sensor. I'm going to click that play button and rise it pretty quickly. There we go. And we're going to slow it down and then come backwards. Okay, so as you can see, I tried going quickly, but it didn't really get there. Then there was a few spikes in the data. Let's not worry about that. But
it's a great activity with students actually walking towards and away from the ranger.
That's exactly right. Yes, that's exactly right. Yes.
Stephen,
so
just
of course,
wondering. A couple of people have asked. Are you also going to show us how the data can be transferred into the standard lists and spreadsheets page, and how we could do a data stats plot from there?
Yes. Yes, sure. I'd be happy to do that.
Yep, this is good. This is good. Yeah.
This is good. Is it all? This is a lot of fun, isn't it?
It's a tough one to do over a webinar, mate. But I've just asked a poll in the background who would like to see you do this at a conference session, and we're getting a fairly enthusiastic response. So you might have a live gig coming up. Yes.
Oh, that's awesome. That's great to hear. Okay, so as some of you have asked, according to Brian, you want to transfer this data that you've got into a list and spreadsheet. That's quite simple to do, really. So I'm going to do something similar again. Hold it there. Increase the distance. Oh, that doesn't look too good. I think I might start again. Sorry about that. Let's do that. I'm just a bit slow this time. There we go. Okay, that's not too bad.
In the background.
You can hear the clicking as well?
Yes.
Yes.
It's come through on my phone, yeah.
That's excellent. Okay, so let's not worry about that spike over there. But if you'd like to take that position time data and put it into a list and spreadsheet app, all you have to do is go to Doc, Insert, or you can, of course, use Control-I, and then go to List and Spreadsheet. Then when you go up to A, you can press the var button, and then link to, and then run one.time. So what that does is it copies all the time values. Of course, we're doing 20 samples a second, so that's 1/20th of a second per sample. So there's 1 and 20, there's the second sample, third sample, etc. Then you can go to the first row in B and do the same thing again. var link to run one position. And there we go. There is the time value versus the relevant position value. And then, of course, you can go to menu, statistics, stat calculations, then do your stats with that. You can get the median, mean, median, mode, etc., etc. Is that what you wanted, Brian?
Yep, that's part of what we've been asking there. It can also come straight out of the data quest. It sends it to lists, but
it does.
It's stored in those lists. Yep.
That's correct. Yeah.
But I'm not going to push you. I'm not going to push you in directions you haven't gone there. Where are we? If we click on, is it the calculator down to the bottom right?
Yes. That one. Oh, there you go.
Sorry, on the left panel, down at the bottom right of that. Yep. So the store there, and I think it actually happens when you exit that program. It stores it.
It stores it. Okay, fair enough. Yeah.
Yep.
Okay, but yeah, I mean, my use of the CBR has been quite basic, as you can see. All I've done is use it for measuring movements versus time, and then doing linear regressions with that. So again, as I said before, the CBR is a really versatile instrument, and it beats some equipment that you can get for quite a few magnitudes more in price. In terms of something that's quick and easy to use with students, the learning curve is very.
Throw that out there? Somebody did ask, what do they cost? And I was just starting to write an answer that I don't remember so long ago that we bought them. You're saying CBR
That's
2,
right.
I bought CBR 1. The standard answer is talk to your calculator supplier, because that's
correct.
They're the people that provide it. But I can't remember if anyone does recall and wants to type that into the chat. But I don't know. It wasn't a lot. I think it was less than the cost of a calculator. I'm not sure.
That's exactly right. Yeah, it's on average it tends to be about lesser than the calculator, which is awesome. So you can get one CBR for the class set, and that's more than enough. And then the teacher can demonstrate an idea, and then students can take turns to use it themselves as well. So it's really cool stuff.
And the beauty being that you can plug it into your teacher computer. and put it up on the
Correct.
whiteboard. So, yep, like what you're doing here, of course. Yep.
That's exactly right. Okay, so I'll put an end to the clicking that you can probably in the background. There you go, the clicking has stopped. So the CBR has done its thing. Now let's move over to some nspire demonstrations. I'll do this very quickly in the interest of time. This is an activity that you can run with the students. Of course, this file will be made available to you on a later date. But a common idea that you'd like to bring students to look at is the relationships that you get between distance or displacement and velocity and or acceleration. So what I've got here basically is one question where you get a velocity time graph, and then what I'm going to do is I'm going to get the area under that graph and plot that along with time as we go along. And then the second one, I've got a displacement function, and I'm going to get the velocity out of that. So as teachers, we know quite easily what the relationships between these things are, but for the students, it might be a bit hard for them to get an idea of that. So using a demonstration like this can make the difference just enough. So I've got a scenario here where I've got a hybrid function. So we've got a car that starts at rest, speeds up to a velocity of 10 meters per second, takes 20 seconds to do that. It then continues at this velocity for another 20 seconds, and then takes 30 seconds to slow down after that. With a bit of mathematical algebra, you could get the hybrid function for that. I'm not going to dive into detail about that, but this is the hybrid function. So in case you're wondering how do you get a hybrid function, what you could do is press the template button here, which is next to the catalog. You press that, and this option here it's got three pieces there, I guess, for the piecewise function. But when you click on it, the calculator does ask you how many pieces would you like. So when I made this, I used 3 pieces, and I gave the respective domains for them. The question now is use areas to analyze the total distance. So this is a velocity time graph, as you can see here. It's a trapezium basically. And what I'm going to do is I'm going to grab that big red dot at the bottom and move it from left to right. And then what's going to happen on the right-hand side is it's going to generate the displacement function. So let's get into that. So I'm going to grab this point, move it left and right. And as you can see, as the area increases, of course, at the top, I've got the time value, which is 18.6, which is currently the time value of the red dot. And then the 86.6 is the integral from 0 to the particular t value under this entire function. And 86.6 is the current displacement of the car. So if I keep grabbing that and I keep moving on, what you can see is as we move from left to right, the calculator is basically populating the screen with all the different area values that we're getting. So what I've got here is the displacement function, d of t, with respect to time. Of course, I could call that x of t as well. But yeah, that right there is the displacement function as time goes on. So basically what I did was I created a data capture. So over here, I'll just clear those columns there. In here is the current time value. Over there is the current area value. And what happens is as I move this point left and right, each point I move it to creates a new t value and a new displacement value. So when I move it left and right, it goes and populates this table with every single data point. And as it's populating the table, it goes and creates this graph. It's a really strong visual aid to help students identify the relationship between a velocity time graph and the displacement time graph that creates it. So
I really like that. Yeah. Yep.
It's really nice. Yes. So yeah, I will quickly.
We're on time. I just said, yep.
We're on time. Excellent.
Yep.
So I will quickly finish off with. I'll quickly finish off with a position graph being given, which is a displacement. It's a normal cubic there. And what we're going to do is we're going to demonstrate the velocity function as time goes on. So again, this is the graph of the displacement xp of t versus t. My time is currently at 0, and my velocity is at 0 as well because the gradient is 0 there. Like my previous example, I've again got a data capture set up over here. It's all set up in automatic data capture. So currently I've got time of 0, velocity of 0. So going back there, I'm going to grab that red dot and move it right. The way I've set this up is I've drawn a tangent as well to the graph, and not only I've got the tangent, I've also got the gradient of the tangent being tracked as I move the point. So again, as I move the point, what's happening is this gradient is then getting transferred as a y value to the green graph on the right-hand side. So what you can see is the gradient increased up to a certain point, and then even though it's still positive, it starts decreasing until it gets to a maximum where the gradient is 0. And then again, you can bring a discussion about that being called a stationary point. And why it's called a stationary point? Because the velocity is now 0. So then you can pause your discussion there, and then again grab the point and take it down, and you can see that the velocity is increasing in the negative direction at a faster rate. And then you can see that little space over there. So you can grab the point, of course, and then sort of fill in the data as best as you can. And there you go. This is the position versus time graph. That is the velocity versus time graph. And then you can, of course, verify this via differentiating the position function and then verifying the analytical solution with the data that you've just captured there. Okay, I think that's enough for my session. Thanks again for tuning into that.
Terrific. Thanks, Stephen. And that data capture, once again, a really clever idea. We're getting comments in the chat there that people really like the linking there. It's a very powerful visual. So I'll just quickly run us out here. Thank you, of course, to both our presenters, Stephen Crouch, who we've just heard from. Can I just point out also that Stephen ran a webinar for Maths Methods, or was one of the presenters in a webinar last week on Maths Methods. You can see that on the webinars on demand, where Stephen showed a lot more on optimization and simulations using the data capture feature. So if you would like to see more of that and haven't yet seen that webinar, I would absolutely encourage you to do so. Thank you also to our first presenter this evening, Sanjeev. And Sanjeev, I ran a poll in the background. People were very impressed with the 3D graphing. Looks like there's more work for you there. People would like a webinar on that, exclusively on 3D graphing. Stephen, we need to have you back at MavCon or the LEC to show us the CBR live.
Yep,
so what's happening there? Thank you.
That'll be a lot of fun,
Thank you for your participation in the polls and your questions throughout the event. This is your last opportunity to type in your gratitude, expressions of thanks, or any last questions that we will see in the chat features. A reminder, please, to fill in the feedback that you'll be taking to after the event, and a reminder that you will be getting shortly a copy of all these lovely files that you've seen. And I encourage you to look through them and deconstruct them, have a look and see how they were made so that you can use with your students. If you wish to view this again, either through our website for webinars on demand or through the YouTube channel, the links are on your screen. And we hope to see you again at one of our upcoming live webinar events. For now, it's good night to all. Thank you to our participants, and thank you to both presenters, Stephen and Sanjeev. Cheers to all.
Thanks, Brian. Thanks, Sanjeev.
Thank you, Brian. Thanks, Stephen.